Now you will remember that we talked about uniform circular motion, and in uniform circular motion we have an object that is rotating in a circle with a constant speed, which is equal to angular speed omega times r, the radius of the circle. The position vector is r hat. The velocity vector is omega r theta hat at any instant in time, and the radial acceleration is minus v square over r hat. It's pointing towards the center. Now, according to Newton's second law, if there is an acceleration, we must have a force that is responsible for this acceleration. So if we have an object with mass m attached to a string performing uniform circular motion around the center, this force, which is responsible for the centripetal acceleration, that is mass times the centripetal acceleration, or mv squared over r, in this case is tension, and it is the centripetal force. Now remember that if the object rotates, it makes one full circle in a period t, then the angular speed is omega equals 2 pi over t, and the speed of the object, the tangential velocity magnitude, is 2 pi r divided by t, where r is the radius of the circle. Okay, so in this video, we're going to try to identify the centripetal force that's responsible for the circular motion. So here is the first example. A small ball of mass m is suspended from a string of length L. So you can see that we have a string of length L. There is a ball that is suspended from the string. The ball revolves with a constant speed v in a horizontal circle of radius r as shown in the figure. So the ball is making uniform circular motion on this horizontal plane with a radius r, and you can see that because this is 90 degrees here, there is going to be a relationship between L and R, considering the angle theta with the vertical axis. Because the string sweeps out the surface of a cone, so you can see that this is going to be completing a cone here, the system is known as conical pendulum. Find an expression for V in terms of geometry in the figure. Now, what I'm going to do is I'm going to draw a free body diagram for this ball. So I have to identify the forces acting on it. The first force is the tension. The second force is the weight mg that is pointing down. Okay, so as you can see that it's performing uniform circular motion under the influence of tension, which makes an angle theta with the vertical. So you can see that this theta is also this theta, and we have the weight of the ball, mg, pointing down. Okay, so if this is our y-axis and this is our radial axis, r and y-axis, two orthogonal axes here, the net force on the y-axis must be equal to 0 because the ball is moving on a horizontal plane. Okay, so the ball moves on the horizontal plane, which means there is no motion on the y-axis. So what is the net force on the y-axis? It's t cosine theta minus the weight mg. So this must be equal to 0. Therefore, I can see that the tension is mg, the weight of the ball, divided by cosine of the angle theta. So on the horizontal plane, I have uniform circular motion on the horizontal plane. And now I can write the net radial force. Well, as you can see here, it is minus t sine theta. Why minus? Because I define r hat pointing in this direction. So it is the projection of tension onto the radial axis is pointing towards the center, so in minus r hat direction. So this is mass times centripetal acceleration. So that is minus m v square over r. So if I substitute for tension mg over cosine theta, so mv square over r, the magnitude of the centripetal force must be equal to tension mg divided by cosine theta multiplied with sine theta. So the mass will disappear, and I will find that V is equal to square root Rg sine theta over cosine theta, which is tangent theta. Now at this point, I'm careful about the problem statement, an expression for V in terms of the geometry in the figure. So that is in terms of the length of the string. And I can notice that from this right triangle that we see here, this right triangle, L cosine theta is here, L sine theta is R. So R, the radius of the circle, is L sine theta. So I can write my final answer as V is equal to square root LG sine theta tangent theta. Okay, so in this problem, we have identified the centripetal force to be the component of tension on the radial axis, which is T sine theta. So T sine theta equals mass times centripetal acceleration, which is pointing towards minus r hat, so minus mv square over r. And therefore, I can see that the speed is related to the radius of the circle and tangent of the angle theta. And also, the radius of the circle is related to the length of the string. So using this relationship, I can write the speed in terms of the geometrical parameters here, theta and L, for this conical pendulum. Okay, now we can move on to our next example. A 1500 kilogram car moving on a flat horizontal road negotiates a curve as shown in figure. If the radius of the curve is 35 meters and the coefficient of static friction between the tires and drive pavement is 0.523, find the maximum speed the car can have and still make the turn successfully. Now, as usual, I have to start with the free body diagram for the car. And as you can see here, there is the weight of the car, the normal force that is exerted by the horizontal road. And then we need a force that is going to act as our centripetal force, and that will be our static friction pointing towards the center. So this will be our free body diagram. It has components on the y-axis and components on the radial axis. So we identify the centripetal force for the uniform circular motion on this flat horizontal road is static friction Fs. The net force on the y-axis must be equal to 0 because it's moving on this horizontal road. It's not flying away. So normal force minus mg is equal to 0. Therefore, the normal force is equal to the weight of the car. The net radial force will be the friction force pointing towards the center minus Fs r hat direction. This will be equal to minus mv square over r, our centripetal force. Now, the static friction has a maximum value, which is m over r maximum value of v square, and that should be equal to coefficient of static friction times n, which is coefficient of static friction times the weight of the car. Now, we can write this as m v max square divided by r is equal to coefficient of static friction mu s times mg. M's will cancel, and we will find a maximum speed for the car to be square root mu s r g. Now we can substitute the numbers that we have from the problem statement into this answer. So that will give us for V max square root 0.523. The radius was 35 meters, so it is 35 multiplied with 9.8 meters per second square, and that gives us a numerical answer for Vmax 13.4 meters per second, since we're using SI units. Okay, so this was an interesting example in the sense that it is the friction force that is responsible for the centripetal acceleration, that is static friction. So as long as the car does not exceed a maximum speed, the static friction can keep the car on track following this rotation, following the circular path on the horizontal road. So we have identified three forces: normal force, weight, and static friction. And static friction maximum value basically gives us the maximum value the speed can have, which is square root mu s r g. And numerically we find this to be 13.4 meters per second. Okay, so let's have a modification on this problem. A civil engineer wishes to redesign the curved roadway in such a way that a car will not have to rely on friction to round the curve without skidding. In other words, a car moving at the designated speed can negotiate the curve even when the road is covered with ice. So when the road is covered with ice, friction will be zero. Approximately. So such a road is usually banked, so it is tilted, which means that the roadway is tilted toward the inside of the curve. As you can see from the figure, there is a tilt angle theta. Suppose the designated speed for the road is to be 13.4 meters per second, which is the answer from the previous problem, and the radius of the curve is 35 meters. At what angle should the curve be banked? So you can see here, this is our car that is performing uniform circular motion on a banked road, and here is our angle theta. So if we drop a perpendicular here, you can see that we have the car normal force to the car from the road is going to make an angle theta with the vertical. So that's what I show in the free body diagram here. I have a normal force making an angle theta with the vertical axis. There's the weight of the car. There is no friction because the road is covered with ice. This is y-axis and this is the radial axis. Now the net force on the y-axis must be equal to 0. Now you can notice that because the road is tilted, on the y-axis I have a component of the normal force, and cosine theta minus mg equals to 0. So this gives us a normal force, which is mg divided by cosine of the angle theta. On the other hand, if I write the radial force, net radial force here is pointing towards the center, which is minus n sine theta, and that is equal to minus mv squared over r, minus because it's pointing towards the center, and r hat is basically pointing radially outward from the center. Okay, now so we're trying to find the angle with which the curve should be banked. So for the normal force, we're going to substitute mg over cosine theta, and the minus signs will cancel here. So we can see that the normal force is mg over cosine theta. Now normal force sine theta equals to mv squared over r, mv squared divided by r. The mass is not important here, mass cancels. So I find that I have tangent theta, sine theta divided by cosine theta. So let me continue here. Tangent theta is equal to v squared divided by rg. So the angle theta with which we should tilt the rod is tangent inverse v squared, so square of the designated speed, divided by radius of the circle and the gravitational acceleration g. So this will give us theta equals tangent inverse 13.4 parentheses square, that is the designated speed, square divided by 35 meters, 9.8 meters per second square. So this is our gravitational acceleration. So that ends up giving an angle of 27.6 degrees for the tilt angle. Okay, so the idea in this example was to replace friction with another force. And we have a special situation where the road is covered with ice. We don't want to rely on friction. The friction is almost zero here. Therefore, we use the tilt angle and the projection of the normal force from the road onto the radial axis in order to account for the centripetal acceleration. So that is n sine theta equals mv squared over r, and we find the normal force in terms of the weight using the net force on the y-axis to be zero because the car is not moving on the y-axis. And by setting a normal force sine theta equals mv squared over r, we can determine the angle theta given in terms of the designated speed, the radius of the circle, and the gravitational acceleration g. Okay, let's move on to the next example. Once again, we have another modification on this problem. A car rounds a banked curve as in the previous example. So we have this angle theta, we have the banked curve. The radius of curvature of the road is capital R, the banking angle is theta, and the coefficient of static friction is mu s. So we have both the tilt angle and the friction acting in this case. Determine the range of speeds the car can have without slipping up or down the road. Find the minimum value for the static friction coefficient mu s such that the minimum speed is 0. So even if I have a minimum speed of 0, the car will not be sliding down. Okay, once again, the first task is to draw the free body diagram for the car. We have the normal force, which is making an angle theta with the vertical. So that is the same thing. Now we have the weight mg that is pointing down. Now the car can slide up or down. So we on this inclined plane. So we have a static friction that can point either up if the car is trying to slide down, or down if the car is trying to slide up. So we can draw two different scenarios here. In any case, you can see that the components of these friction forces on the radial axis will have some contribution on the centripetal force. So I'm going to start with the scenario where I have the static friction is pointing up in the inclined plane here. So that is this red scenario. When I write the net force on the y-axis, so this is net force on the y-axis, this must be equal to 0 because the car is not moving on the y-axis. So that is n cosine theta, that is pointing up. And then I have a component of the static friction Fs sine theta that is pointing up, and then I have mg that is pointing down, so this must be equal to mg. So you can see that my static friction Fs will be, in this case, equal to mg minus n cosine theta divided by sine theta. And this should be less or equal to the coefficient of static friction mu s times the normal force n. So that is the force that is perpendicular to the friction force. So this gives us basically the following inequality. We can write mg is less or equal to mu s sine theta, so in n parentheses, mu s sine theta plus cosine theta, or we can write the normal force to be greater or equal to mg divided by mu s sine theta plus cosine theta. Okay. Now I'm going to write the net radial force acting on the car. So the net radial force Fr will be, as you can see, n sine theta is pointing towards the center, so it's minus n sine theta r hat, so minus n sine theta. And then I have the static friction, the red one, that is pointing radially outwards, so this would be a plus Fs cosine theta. So this would be responsible for the centripetal acceleration minus mv square over capital R in r hat direction. Now what I'm going to do is basically change the sign here. So this will be a plus, this will be a minus, this will be a plus. And I note that if I write this, if I isolate Fs here, the static friction Fs should be equal to 1 over cosine theta times n sine theta minus mv square divided by capital R. So this is our static friction, and this can be rewritten as n times tangent theta minus mv square divided by capital R cosine theta, and that is less or equal to mu s times the normal force. So if I put this in the normal force parentheses, this is normal force tangent theta minus mu s is less or equal to mv square divided by r cosine theta, and that gives me n tangent theta minus mu s from the statement I had about the normal force here. Normal force is greater or equal to mg over mu s sine theta plus cosine theta. Basically, for n tangent theta minus mu s, I can multiply this one with tangent theta minus mu s, the right hand side and left hand side, in order to obtain another inequality for n tangent theta minus mu s. So this is coming from the previous inequality that we have obtained here. So I'm multiplying this with tangent theta minus mu s. This is greater or equal to mg tangent theta minus mu s divided by mu s sine theta plus cosine theta. So as you can see, I have two inequalities. One says n times tangent theta minus mu s should be less or equal to mv square over r cosine theta. The other inequality says it should be greater or equal to mg tangent theta minus mu s divided by mu s sine theta plus cosine theta. So putting these two pieces of information together, I can basically write mv square over r cosine theta should be greater or equal to n tangent theta minus mu s, which is greater or equal to mg tangent theta minus mu s, so divided by mu s sine theta plus cosine theta. So this gives me the following result. Because the masses cancel here, I find that taking the square root of both sides and isolating v should be greater or equal to rg cosine theta tangent theta minus mu s cosine theta divided by mu s sine theta plus cosine theta square root. And if I divide the top and bottom with cosine theta here, this can be written as v is greater or equal to rg tangent theta minus mu s divided by mu s tangent theta plus 1, because I have divided top and bottom with cosine theta and square root of this quantity. So if v is greater or equal to this, that means the minimum speed I can have, v minimum, will be square root of rg tangent theta minus mu s divided by mu s tangent theta plus 1. So this is my minimum speed. So this scenario, the red scenario for Fs pointing up, gave me the minimum possible speed I can have. Now I'm going to work with the other scenario where the static friction is pointing down. So that is the blue scenario here. So let me repeat this exercise for the blue scenario. Once again, I can write the net force on the y-axis should be 0. This will give me, let me check, n cosine theta minus fs sine theta minus mg equals 0, or this can be written as n cosine theta minus fs, this one is the blue scenario, fs sine theta equals mg, second scenario. So this gives me for the static friction, let me keep this blue, fs is equal to n cosine theta minus mg divided by sine theta, which is less or equal to mu s times n. So I can write n cosine theta minus mg is less or equal to mu s times n times sine theta, or I can write this in n parentheses, n times cosine theta minus mu s sine theta is less or equal to mg. So this gives me a normal force that is less or equal to mg divided by cosine theta minus mu s sine theta. Now I come to the radial force. The net radial force here will be the projection of n onto the radial axis, n sine theta pointing in minus r hat direction, fs cosine theta pointing in minus r hat direction, which is equal to centripetal force minus mv square over r. So this is minus n sine theta, and then I have minus fs cosine theta equals to minus mv square divided by r. So if I get rid of the minus signs here, this is plus plus plus. I can isolate fs here. So fs can be written as 1 over cosine theta parentheses mv square over r minus n sine theta. So this must be less or equal to mu s times the normal force. So I find that mv square divided by r cosine theta minus n times sine theta over cosine theta becomes tangent theta is less or equal to mu s times n, or I can write this as mv square divided by r cosine theta is less or equal to, in normal force parentheses, mu s plus tangent theta. So since I have this inequality and this inequality, I will multiply this one with mu s plus tangent theta in order to obtain this form here. So also I have n less or equal to mg over cosine theta minus mu s sine theta. So n times mu s plus tangent theta is less or equal to mg times mu s plus tangent theta divided by cosine theta minus mu s sine theta. And putting this inequality and this inequality together, mv square over r cosine theta is less than this, but it's also this is less than this. So mv square over r cosine theta should be less than this quantity. So we can write mv square, putting these two together, divided by r cosine theta should be less or equal to mg times mu s plus tangent theta divided by cosine theta minus mu s sine theta. Okay, so if we take this one step further to isolate v in this scenario, we're going to have v square less or equal to rg cosine theta mu s plus tangent theta divided by cosine theta minus mu s sine theta. So this is basically isolating v square by multiplying with r cosine theta, getting rid of the masses here, and we're going to see this result. And therefore, if I divide the top and bottom with cosine theta, I see that v square is less or equal to rg mu s plus tangent theta, that is the top divided by cosine theta, and the bottom divided by cosine theta will give us 1 minus mu s tangent theta. So this is v squared less or equal to this quantity, so I find the maximum speed I can have is rg mu s plus tangent theta divided by 1 minus mu s tangent theta square root, because it was v squared. So this is my maximum speed. Okay, so this completes my answer to part A of the problem, which is determining the range of speeds the car can have. I have found a minimum speed and a maximum speed. Now in part B, the problem asks me to have a minimum speed of 0 and to find the mu s that will satisfy this condition. Now the minimum speed was rg tangent theta minus mu s divided by 1 plus mu s tangent theta. Now if this is going to be 0, this will imply that the coefficient of static friction must be equal to tangent theta. So if this is satisfied, then we can have a minimum speed of 0, and even so, it will not be basically sliding down. It will not be slipping down the road even with 0 speed. Okay, so to summarize, we have modified the previous problem where we had a banking angle of theta, so the normal force component on the radial axis was responsible for centripetal acceleration, now to include static friction as well. Now the static friction can cause sliding up or down this tilted road, and so we have to consider two scenarios, one static friction pointing up, one static friction pointing down. And these two scenarios basically gave us a minimum possible speed and a maximum possible speed for the car, and setting minimum possible speed to 0, we find the requirement on the coefficient of static friction to be equal to tangent of the angle theta. Now we're going to look at one more example. An amusement park ride consists of a large vertical cylinder that spins about its axis fast enough that any person inside is held up against the wall when the floor drops away. The coefficient of static friction between the person and the wall is mu s, and the radius of the cylinder is capital R. Show that the maximum period of revolution to keep the person from falling is given by this expression, t is equal to 4 pi square r mu s divided by g square root. And in part B, if the rate of the revolution is made to be somewhat larger, what happens to the magnitude of each one of the forces acting on the person, and if the rate of the revolution of the cylinder is instead made to be somewhat smaller, what happens to the magnitude of each one of the forces acting on the person? How does the motion of the person change? Okay, so let's start with free body diagram for the person. The person is held up against the ball due to friction, static friction. The weight of the person is pointing down, and the normal force is pointing radially inwards. So this is our y-axis, this is our radial axis. So we can write the net force, the net radial force, to be equal to minus n, because it's in minus r hat direction, which is minus mv square divided by r. So our normal force is equal to mv square divided by R, capital R. The net force on the y-axis must be equal to 0 because the person is not sliding up or down. Then the static friction Fs minus mg must be equal to 0. The static friction is equal to mg, which must be less or equal to mu s times the normal force. So this requirement gives us mg should be less or equal to mu s times mv square divided by capital R. And we can see that the m's will cancel here, and we will find capital R g divided by mu s is less or equal to v square. Now I want to remind you that v is also equal to 2 pi r divided by the period of revolution, 2 pi r divided by t. So v square is 4 pi square r square divided by t square. So you can see in this inequality that one of the r's will disappear, and I will find that taking t squared to the other side, t square should be less or equal to 4 pi square mu s times capital R divided by g. So therefore, the maximum period I can have in this case is equal to 4 pi square capital R mu s divided by gravitational acceleration g square root. Now part A of the problem was basically showing that this is the maximum period of revolution necessary to keep the person from falling. So that has been achieved. Now I try to understand what happens if I change the speed. Now if the rate of revolution is made to be somewhat larger, that means I have a maximum period, so maximum period I have a minimum speed. So if I have a speed that is greater than the minimum speed, which is 2 pi r divided by the maximum period, T max, then the normal force, which is mv square over capital R, will become larger. And the static friction Fs is equal to mg, doesn't change. So this condition is satisfied, and the person is safely held against the wall. So if I have a period that is less than the maximum period, or a speed that is greater than the minimum speed, then the normal force will be larger, but that will be the only effect, and the static friction, which is less or equal to the mu s times the normal force, will keep that condition by having Fs equals mg, so that will not change, and the person will be safely held against the wall. Now in part C, if I have a speed that is less than the minimum speed, then the person is in danger. So the period is larger than the maximum period. Then the normal force, which is mv square over r, it will decreases. The maximum friction I can have, mu s times the normal force, decreases below mg, the weight. So what happens is that the person starts sliding down, and the static friction will turn into kinetic friction. Okay, so in this example, we have an amusement park ride. This person gets inside the cylinder. The cylinder starts spinning about its vertical axis, central axis here, and the floor drops away. Now, what should be the maximum period of revolution, as we have shown equivalently the minimum speed, tangential speed I need to have to keep this person safely held against the wall. And if I have a speed that is greater than the minimum speed or less than the minimum speed, what happens? So first, my free body diagram for the person shows that the normal force is the radial force here. It's mv squared over r, and the static friction is the friction that keeps the person from falling on the y-axis. So static friction is equal to mg, and it should be less or equal to mu s times the normal force. So if mu s times the normal force becomes less than mg, then we're going to have the friction force not being equal to mg, and therefore this person will the weight will win. The person will start sliding down. So setting mg less or equal to mu s times the normal force mv squared over r, and recognizing the relationship between the period and the speed, 2 pi r over t is the speed, we find the maximum period, the same expression given in the problem. If we have a velocity that is tangential velocity that is greater than the minimum, then we will have the normal force increasing, and Fs should be less or equal to mu s times the normal force. It was equal to mg, and this condition, mg less or equal to mu s times the normal force, will be easily satisfied. The person is safely held against the wall. If the speed is too low, then we have a normal force which is too low, and the maximum value of Fs becomes too low, less than mg, and the person starts sliding down, and the static friction will decrease further to kinetic friction. Okay, so basically these are the 5 examples we have gone through to investigate the force that is responsible for the centripetal acceleration in the circle